Hello, everyone. Well, look, today some of the hottest topics beside the COVID-19, which is the era that we are recording this webinar in, are energy storage and energy saving, batteries and battery power density. These topics have become the flavors of the month, along with the development of hybrid vehicles in which energy restoration is of quite a significant value and importance. However, non-electrical sources of energy are often overlooked in that context. So today's webinar is scratching the surface on one of the oldest methods of energy conservation, being hydraulic energy conservation, and the use of hydraulic accumulators in that area. Although today hydraulic accumulators are used for a number of different applications and purposes, the primary function of an accumulator remains to be energy storage. So welcome to another episode of HYDAC webinar. My name is Ali Nijat. I'm HYDAC's National Development Manager for Industrial Hydraulics. Before we start and get to the content, I just wanted to give my colleagues Steve Nolan and Pravir Dhaliwal a big shout out. They opted in to come on board, help me with the content of this webinar, and they were a great deal of help as part of the process. Today's webinar is, as I mentioned earlier, is hydro-pneumatic accumulator applications. As part of this webinar, what we will look at will be a bit of history and origin. I'm not going to give you a history lesson, but it's always good to see the journey since the beginning till now. We'll have a look at the industry sectors where we've got hydraulic accumulators installed and commissioned, are in use quite commonly. And then we have a look at some of the selection criteria. We've got different types of hydro-pneumatic accumulators, and of course, for each one of them, there's a different type of application. And as for selection criteria, there are different parameters that we look at and we consider. So we look at all of those as well. We look at some of the applications of hydraulic accumulators, the most important ones, obviously. And at the end, we'll finish off with some simulation programs and examples of each one of these applications. So we've got some really exciting contents for you ready. Sit tight and enjoy. So as for history and origin, probably you know that HYDAC are the largest manufacturer and producer of the hydraulic accumulators in the world. So just looking back at where we started, back in 1963, that's when HYDAC was founded with the name of HYDAC, a hydraulic accessories company. Then in 1968, we produced our first hydraulic accumulators, and in 1988, that division of HYDAC changed its name to HYDAC Technology. So today, hydraulic accumulators are when we're talking about the production in Germany, the design departments and global supply management are done through HYDAC Technology Division. In 2009, we had an exciting acquisition happening with our sister company QHP, the UK-based company who is specialized in supplying accumulators to quite a number of different industry sectors, but most importantly offshore and oil and gas sectors. In 2016 we finished the build of our factory number 2, which is now a designated plant for manufacturing of hydraulic accumulators of all different types and shapes. So a very quick overview of HYDAC's journey to date and when we started and the long way that we've come along. So we all know HYDAC is a German company. When we talk about different production plants, the bladder accumulators are produced in a number of different countries around the world: Germany, USA, the United Kingdom, China, Korea, Singapore, India, closer to home in Australia and Brazil. They are the plants which manufacture bladder type accumulators. Moving on in terms of piston accumulators, and we get to the differences between all these vessels in a few slides, but bear with me for now, just an overview of where these vessels are sourced from. Piston accumulators: Germany, USA, England, India, and China. And with our diaphragm accumulators, we've got fully automated plants in Germany, USA, and China. So it's quite a good coverage across the globe in terms of production and supply. Let's have a look at the industry sectors. That's the spectrum of different industries in which HYDAC accumulators are commissioned, working, and used for. The first one, the mobile technology, we've got the automotive sector, agricultural machineries, forestries, and construction machineries. And by all means, this is not the entire range of industry sectors that we are involved with our accumulators. This is just some of the highlights and the main industry sectors. You will find, accumulators in all sorts of different applications, but these are the headlines of that. The stationary technology or industrial sector, we've got the paper industry, presses, machine tools, mining, iron and steelworks, plastic machineries, turbines, power gen, and marine industry. Then we've got the process technology for oil and gas, chemical industry, food, offshore, fluid pumps, loading stations. When we talk about shock absorption, for example, as one of the primary functions of an accumulator, that becomes quite significant. We'll get to that in a few slides. Aerospace, passenger planes, where it's a landing gear, whether it's for fluid separation, all sorts, helicopters, sports plane, and recreational planes and space flights. And in terms of dealing with the OEMs, obviously there's a division of HYDAC who deals with the supply and of the accumulators to the OEMs, which have supply contracts with HYDAC, and we support that globally through our OEM division in HYDAC technology. Moving on, selection criteria. It's important to understand that when we talk about hydro-pneumatic accumulators, I mean, there are different types of storage or hydraulic energy storage accumulators out there. The old-fashioned ones, there are still some of them out there, is the weight actuated accumulator. That's when you've got a dead weight sitting over a surface, applying force and pressure, induced pressure into a fluid. Typically, the pressure and volume curve looks like that. So the pressure has a direct correlation with the dead weight applying the force on the fluid. Then we've got a spring type accumulator. So as we dispense the fluid out of this chamber and the spring extends, you can see because the spring force decays, we've got less pressure induced by the spring force onto that fluid. And we've got the hydraulic accumulators, hydro-pneumatic accumulators, in which we've got a separating element between two different fluids. So we got or a fluid and a gas in the hydro-pneumatic accumulators. That gas is predominantly nitrogen, and we've got a pressurized gas which induces potential energy over to the fluid side. And as we discharge fluid from the accumulator fluid side, the pressure versus volume curve, or the characteristic curve, is more like an adiabatic curve. So if you've studied your thermodynamics, you're very familiar with this type of curve. So important to know that in this webinar, we're talking about our hydro-pneumatic type accumulators. So moving on, we've all heard about different types of accumulators. We've got bladder type, piston type, diaphragm types, and metal bellows. They all have their own advantages and their own use. With bladder accumulators, when we've got some really high flow rates and high volume range, similar to the piston accumulators, again, they can be of a very large volume. So you can see in terms of volume range, the bladder type accumulators can range to 450 liters. Piston accumulators, we're talking up to 3,300. Diaphragm accumulators are typically a bit smaller, and metal elbows are really customized to the specific application. Pressure range, they can all withstand quite a high pressure range, but certainly when we look at selecting an accumulator for an application, these are some of the basic parameters that we look at in terms of selecting an appropriate accumulator for an application. Also, there are some other decision-making factors. For example, what is that separating element between the gas side and the fluid side, whether it's a bladder in this case, or in a piston accumulator, we've got a mechanical separation element, which is the piston. Diaphragm accumulators, we've got a diaphragm or a membrane. And, with that, obviously, it comes sensitivity against dirt or gas loss and pressure differential between the two elements. So again, some of really broad parameters that we look at when we start selecting an accumulator for an application. So let's get down to the applications. As I explained earlier, the primary function of an accumulator in hydraulic systems, and that's probably the most used type of application amongst all, is energy storage. Now, you can just break it down to different types of terminologies, but effectively what that energy storage means is we've got a certain volume of fluid under pressure. So the fluid pressure and the volume, the combination of the two, translates into hydraulic energy. So we store that hydraulic energy inside an accumulator, and when we need that energy to be dispensed at an appropriate time, we press the release button, and we can get that energy dispensed into the circuit in the form of hydraulic flow and pressure. So now you can label it with different terminologies like shortening response time. That's when we've got accumulators coming to help a hydraulic pump to have a boost, flow for a particular, cycle as part of the machine operation, and helps, shortening response time. We've got energy conservation, emergency standby power, and that's when we've got, accumulators storing some energy. And when there is a failure, for example, electrical power failure, we want to start running a genset of some sort, with a hydraulic motor driving it. Then we dispense some of the hydraulic energy from an accumulator and inject it into that part of the circuit. Auxiliary power source, again, similar to the previous one. Dispensing pressurized lubrications. Let's have a look at some of this arrangement. For example, this one here, that's a blowout preventer arrangement. This is typically for an oil and gas type industry, and we've got quite a significant amount of hydraulic energy reserved in these piston accumulators, so quite a passive type operation. And in case of a blowout prevention, then the energy is released from these piston accumulators into the circuit to do the function that we're expecting from the circuit. Or this is a process type system. As you can see, that an array of accumulators, bladder accumulators at the back of this arrangement here. These accumulators are maintaining a certain amount of pressure on the medium fluid, which is used in a seal support system. For example, in a mechanical seal arrangement, when we've got pressurized fluid behind a mechanical seal, that's where we've got the accumulators predominantly used. Or more industrial type applications. So we spoke about shortening response time. As I said, sometimes for a fraction of a second, or maybe not fraction of a second, but for a few seconds, we need the boost flow injected into the circuit. If you have to deliver that with a hydraulic pump and associated motors and everything, the size of that arrangement becomes quite significant. So we store some energy inside the accumulators, and when we need that fast response for that fraction of a second, the accumulators come to help the hydraulic pump to deliver more flow into the circuit. Or similar to this one, this is an accumulator bank on a ball mill lubrication system. So when you've got a sag mill, when you've got a ball mill, they all come with their own lubrication systems. If there is a power failure or a pump failure of some sort, the ball mill doesn't stop just immediately. We need a certain amount of fluid stored under pressure, so we can, until the ball mill finishes its cycle without primary lubrication system running, we can supply some lubrication oil into the arrangement. And an accumulator bank like that, which stores quite a significant amount of volume of oil, helps us with that function. Now, some simulation examples. This is where things get quite exciting. So typically, clients come to us and ask for a question like this. It is a very common type application. So they say, all right, I need a bladder accumulator, which has to operate between 300 bar and 100 bar. And these pressures are corresponding with the state of the bladder. So you can see this is where we've got that bladder is squeezed and the gas under pressure, up to 300 bar energy stored in the bladder, and the equilibrium on the fluid side, we've got the same 300 bar. And the 100 bar is when the bladder is fully deflated to its P1 or minimum pressure set point. The amount that the bladder accumulator will dispense is pretty much this orange area, as you can see, it's marked here. So they come and say, all right, we want to dispense around 5 liters of fluid within 30 seconds between the pressure of 300 and 100 bar and the temperature of 10 degree to 40 degree. That's ambient temperature. So this is the most simple type application that we often received. For that, we use our ASP, or Accumulator Simulation Program, ASP Lite module. That module is available on HYDAC website, or I'm pretty sure you've got our HYDAC Tools app. You can access this module free of charge. It's a very handy calculator that is available to you, that you can just punch in these parameters in there, as you can see. So the P2, the maximum pressure is 300 bar, P1 is 100 bar. We've got the operating pressures, or ambient temperature, 10 and 40 degree. We've pre-charged the accumulator to 83 bar, so that's the pre-charge pressure at 20 degrees Celsius. That's the 20 degrees Celsius there. And then we've got, obviously, we can change the units of measurements. Again, sorry, this is not quite a lesson on how to use the Accumulator Simulation Program, just a brief overview to put it in context as to how we deal with an example like that, So we put all those parameters in. The delta V is the amount of fluid that we want to dispense from the accumulator. Put that in there, click on the V0. V0 is the gas volume, or in simpler terms, the accumulator volume. And then we can calculate the V0. So we need a gas volume, or accumulation volume, of between 19.34 to 23.47 liter. And these volumes correspond with the different ambient temperature. So if you want to be conservative, I know at colder temperature, because of the gas behavior, I will have to use a larger accumulator to deliver the same amount of fluid. Obviously, we've got different types of cycles: adiabatic, isothermal, whether it's a charge or discharge. They all give you different values. So you have to be careful of, what the differences are between an adiabatic cycle and an isothermal cycle. So this is the first and the most simple way of looking at an accumulator application and how to apply it. Now, in a bit more complex context, then is when we've got a combined cycle. So the top part is not changed; it's the same thing. But the second part, it says there is a waiting period of 1 minute until the bladder accumulator is filled again. The pump delivers 50 liters a minute and operates for 30 seconds. The entire cycle takes 2 minutes to complete. So that's where we've got a pump in the circuit as well. It's a combined cycle. So we've got some more advanced tools that we can enter all the pressure and volume data in there. We can calculate the accumulator size, and we can simulate the pressure, volume, and temperature behavior of the accumulator or accumulator station over time. So that software is called ASP5, or Accumulator Simulation Program 5. A couple of snapshots from how it works. Obviously, we've got the inlet or the input section where we've got all those parameters here. Remember, P2 300 bar, P1 100, pre-charge 83, and temperatures. So we can put that all in there. Then moving on, we can start putting the cycles. That's the accumulator cycle, as you can see, and it's the pump cycle, as it was requested before. We can just, simulate that and factor in when the pump kicks in, when the accumulator has to discharge the fluid and everything. And moving on, we can calculate the accumulator volume here. So once we've done that, we've got a list of accumulators on the right that we can select from, and we choose one of these accumulators and we move on to the simulation cycle. So on the simulation cycle, we can see the pressure graphs, we can see the volume graph, temperature. You can see, the accumulator starts discharging. So that's a P or pressure graph over time. So just if you want to quickly interpret that, the accumulator starts discharging at 300 bar all the way down to 100 bar. Then we've got a period of time before the pump kicks in over here that the temperature within the accumulator starts stabilizing. As we discharge volume from an accumulator, the gas expands and its temperature drops. So as the temperature drops, when we get to that point here where we've got a bit of an idle cycle over there, the temperature starts rising slowly. And at that point, we have the pump kicking in and start charging the accumulator through this cycle back to 300 bar. So this is a very simple example of accumulator simulations. At times, it can actually get quite complex. We've got a number of different cycles happening, different pumps come to the circuit at different times. We are able to simulate that through this program to have a great deal of accuracy, actually. We've done so many different systems using this program. And when we did the factory acceptance test and recorded the data, we came to realize that the result is very, very well calculated, and we can map that result to very precise measures to the graphs that ASP5 generates. So a very useful tool. We've got the in-house expertise to use that, and we can come up with some really good results there. Now, moving on to other applications of hydraulic accumulator. Another famous one is pulsation dampening or pulsation damping. Now, please do not mistake this with what we've got in our traditional, for example, suspension system. Pulsation damping is when we've got a reciprocating pump. As the pump operates, it creates some pulse waves within the fluid on both the suction side and the pressure side. So this illustration here puts that in perspective. So we've got a reciprocating pump, as you can see here, so back and forth, and we've got a diaphragm arrangement. So this is a diaphragm type pump. As it picks up the oil from the suction side, you can see there's a pulse wave, because every time it starts pushing the fluid back to the pressure side, the suction stream is interrupted then. In that case, we've got an accumulator to stabilize that. So the incoming fluid will be stored in an accumulator, waiting for the next cycle to come up. And as the next cycle come up, that fluid is then dispensed from the accumulator. But as you can see in this area here, the inlet suction is pretty much uninterrupted. On the fluid side, pretty much the same. Once the pump is busy picking up oil from the suction side, the flow on the delivery side is now interrupted. So you can see that accumulator works very well to absorb some of that pulsation. So again, if you want to have a look at the curves, we've got the pressure and time curve. As you can see, all this pulsation with quite a high amplitude happening over time. Now, if I just put a simple standard bladder accumulator in there or diaphragm accumulator in there, we can reduce that amplitude to a significant level and make the flow stream a bit more laminar and uninterrupted without any pulsation. But if we use a proper pulsation damper arrangement, which we'll get to that again in a few slides, then you can see the spikes are nowhere nearly as significant as what it was before without that pulsation arrangement. So in systems, again, so it's also important to understand that there is a limit to that. If the frequency of these pulsations are very high, we can't quite use a pulsation damper, and that's when we look at different types of accumulators. We get to that in a few slides again. So if you want to calculate the pulsation, obviously we can go through the formulas. I encourage you to have a look at these formulas. They're all listed in the HYDAC accumulators catalog. I'm an engineer, so I'd love to understand everything from basic principles and then use other tools that are available to me. But you can see, so this is the accumulator volume in a pulsation damper arrangement. You know, it's a function of stroke volume and the frequency and the residual pulsation. That's pretty much how that's the percentage of the pressure spike amplitude that we want to reduce the pulsation to. So you can put the numbers in there, but typically customers come to us and say, all right, I've got, for example, a diaphragm pump here, as you can see in this arrangement there, and I want to put an accumulator on the outlet to reduce the residual pulsation to plus minus 1%. So that's a very good pulsation damping characteristics. Then we can use the ASP, or accumulator stimulation program, to do the calculations. So typically customers ask, all right, what type of accumulator volume or what type of accumulator I have to put in there, and what's the volume of that accumulator, and also determine the theoretical residual pulsation with the selected accumulators. So here is a typical example. Reciprocating pump here, that's the suction side. We've got an accumulator with a suction pulsation damper block arrangement. So as you can see, this arrangement, what it does, it redirects the flow stream into the accumulator. So the accumulator is directly affecting the pulsation in that flow stream. If you don't have that, the pulsation simply travels through inside the pipe without going into the accumulator. And that's what you can see, you know, with that arrangement, we really reduce the amplitude of the pulsation from that curve to this one here. So pump types, we've got, this is a single acting diaphragm pump, flow rate 50 liters per hour, number of stroke 160 per minute, you know, pump pressure 15 bar, pre-charge, typically with pulsation dampers, we pre-charge the accumulators 60%. Temperature 20 degrees, and we want to reduce the residual pulsation to plus minus 1% of whatever it is without the pulsation damper. And the fluid that this pump is pumping is water. So we look at the pulsation damper module of the ASP light. We put in all those input parameters over here. We can change the residual pulsation to different values from plus minus 5% all the way to 2.5%, plus minus 5 being the best, you know. And we can choose whether or not we want to put that pulsation damper on the suction side as a suction stabilizer or on a pressure side. And the software will calculate the gas volume. In this case, 0.097 of a liter. And then we can look at the catalog and choose the right size accumulator. In this case, we've chosen a diaphragm accumulators of 210 bar design pressure and 0.32 liter. So that's obviously larger than that, and with a good safe margin of safety, we can choose that accumulator to achieve that result for us. So in terms of installation, so we spoke about the pulsation damper arrangement, which is a block which redirects the pulsation into the accumulator. If that pulsation damper arrangement is not available to you, an alternative way of doing it is just installing an accumulator in a fashion that the bladder or the diaphragm is perpendicular to the flow stream coming out of the pump. So you can see the flow is just directly acting upon the bladder or the diaphragm here, and the outlet flow is not as good as this one here, but still quite a fair bit of reduction in the residual pulsation there. Now, another application of accumulator is shock absorption. Again, do not mistake this with our typical suspension. This is where we start talking about Joukowsky shock or fluid hammer. A typical application of that is where we've got in refineries, we've got loading arms. You know, when the trucks come over, we've got a big pipe line upstream with fluid in there, and then we've got a loading arm or a loading station to fill up these trucks. And we've got a quick actuating valve. Imagine just a fuel bowser in a petrol station. So what happens is when a fluid, well, obviously when we are refilling these tankers, what's happening is a big mass of fluid is in motion, and all of a sudden when we let go of that valve, of that bowser, or there's a quick actuating valve, the motion of that fluid is forced to stop or change its direction. As a result of that, we get a pressure spike or a surge within the pipeline. Sometimes this surge can be so significant that it can break the pipes, can break the pipe supports, and cause some serious damage to the piping and to the system. That's when we put an accumulator in there to dampen some of that surge. So this phenomena or pressure wave is commonly referred to as fluid hammer. Mr. Nikolai Joukowski, he studied that in a great depth, and he came up with some formulas, and sometimes that shock is also referred to as Joukowski shock. So let's have a closer look at that. So we've got a pipeline full of fluid flowing through, and we've got a close or quick actuating closing element over here. So as we close this element here, the pressure spikes, and at fully closed operation, that's where we get the maximum surge within the pipeline. So that surge will take place and get propagated through the pipeline back to the source and coming back to this closed element. As a result, we get this effect as per this diagram here. So you've got a surge, goes back to the source, come back again, goes back to the source. So if you put an accumulator there, very close to the source of this pulse generation, then we can dampen some of that surge and bring it back to the thresholds of pipeline design parameters. For example, if the pipeline is designed to withstand 16 bar, and if the amplitude of the surge is 18 bar and this is 16, what we want to do, we want to bring the surge value just under this curve here, which is 16 bar, just to avoid damaging the piping. Again, Mr. Joukowski, he came up with these formulas. They're all listed in the HYDAC accumulator catalog. Feel free to have a read through, understand what they are. But again, alternatively, we've got in ASP5, we've got a module which is designated for these particular calculations. Typically, we can calculate the Joukowski shock if the system is fairly simple. If we've got different branches of pipe and different valves and different pumps, that calculations become quite complex. So typically we look at one pump, straight length of pipe of different diameters it can be. We've got a quick actuating valve or a closing element. And as the surge happens, we've got an accumulator installed very close to that valve to dampen some of that surge. So customers come to us and say, yep, we've got a fuel farm. When fuels are loaded into vehicles, ships or vessels, the flow is abruptly interrupted. When the valve is closed, you can let go of the bowser. This sudden deceleration of mass results in pressure shock, which is also referred to as Joukowski pressure shock. By using hydraulic accumulator, we can just reduce this shock. Can you tell us how big that accumulator is? Again, they give you some parameters, including the closing time of the valve. They say it just shuts in 1 second. The pipeline length, 1200 meter in this instance here. The cross sections, the diameter of the pipe, the wall thickness of the pipe and the material, the fluid that flows through this pipeline at a certain flow rate, and the pump information. Then we put that all in there, and we can calculate the critical closing time. That's a time that we've got available before the surge goes back to the source and come back to that closing element. And we can calculate the maximum pressure shock. So in this case, with that example, the maximum pressure shock is 14.15 bar. Previously, we had specified that the maximum pressure that the pipeline can withstand is 12 bar. So we want to put an accumulator to make sure that that excess 2.15 bar is absorbed within an accumulator, and therefore within an accumulator of this size, 71.82 liter. But an interesting factor here is this moving load. 5,473 kilogram of moving load. What it means is, imagine 5.5 ton truck, right? And all of a sudden, I just put a dead ball right in front of it, and this truck slammed that ball. It is pretty much the same effect as we get as we've got a mass of fluid flowing through a pipeline, and all of a sudden, a quick actuating closing element is trying to stop that flow stream. That's how much moving load we've got in that arrangement there. Very interesting. And then obviously we've got vessels of typically larger diameter because the surge is so significant that in arrangements like that we need a vessel of larger volume, and also the inlets of these vessels are a bit different to standard accumulators. You know, they're often larger inlets, so we actually let the surge in, and we don't have any of those poppet arrangements or any restrictions between the flow stream and the bladder inside the vessel. So the design of the inlet is also quite different. Some other applications of accumulators. So we've got noise attenuation, volume compensation, suspensions, and fluid separations. Let's quickly have a look at some of these ones that are important, not probably as common as the other ones, but fairly significant. So first one, silencers. Remember, when we were talking about pulsation dampers, we said at higher frequencies, perhaps above 150 hertz and above, pulsation dampers are not really that effective. The pulsation becomes a characteristic of the fluid, and it conveys itself as a fluid-borne type noise. You know, when we've got volume and pressure fluctuation within the fluid at a frequency higher than 150 hertz, that turns to noise. So in that occasion, then we'll use this arrangement here, which is called a silencer or a noise attenuator, which is working on the principle of expansion chamber. And what it does, it just reflects the oscillation within the silencer, and the majority of the oscillation are dampened, and the outcome is a lower frequency or lower amplitude of noise. So the silencers, they don't have any moving part. It's basically a tube within the channel, so there is no bladder inside, and as such, they're very much maintenance-free type arrangements. Other application is a volume compensation. That's when we've got a large volume of fluid trapped within a metal chamber, for example. We all know that the volumetric expansion coefficient of fluids are greater than their container, in this case being steel. So what happens is, if that chamber is exposed to sunlight, and all of a sudden the temperature from 5 degrees in a cold morning rises up to 80 degrees Celsius around lunchtime, somewhere in Pilbara in the sunshine, what happens is the fluid inside that chamber will expand at a rate which is greater than the expansion rate of its container, and therefore we'll have some induced pressure. So that induced pressure then can be absorbed inside a hydraulic accumulator. Very common, but often overlooked. Interesting application here. So you can see we put the maximum pressure that the system allows, and we can allow it to go up to the minimum pressure, the temperature, the pipe volume. So what it does, it just calculates the expansion of the fluid, calculates the expansion of a chamber. The difference in pressure or induced pressure will be used in sizing the accumulator itself. Next one, suspension or shock absorption in the context of suspension. That's very, very common. You know, we've got the drive terrain of some of the on-road vehicles, for example. That's where we've got an accumulator like this acting upon a suspension cylinder. So calculation of that is not really too difficult either. The way that we traditionally calculate this, we say, all right, so we've got a cylinder on the suspension side, which can have a stroke of certain limits. And within that stroke depends on how stiff we want the suspension system to be. We can set the minimum and maximum pressure within the system. So again, we've got the dispensed volume, we've got the minimum and maximum of the pressure, and we can calculate the accumulator size. Other applications of this is, for example, if you've got a wheel loader, like a bucket suspension in wheel loader is quite important. For example, if a wheel loader is traveling on a very rough surface with the bucket full and up, what's going to happen is that moving load, the momentum of that load will be transferred onto the wheel loader, and it can result in, kind of tipping over the entire machine. So we use hydraulic accumulator to dampen some of that momentum as a suspension. Last but not least, media separation. So that's also not a very common type application, but we get that in different industries. Basically, when we want to pressurize a certain fluid, which is maybe not quite compatible with the pumping system that we've got upstream, you can have, for example, in this arrangement here, you can have hydraulic oil and a hydraulic oil pump applying the pressure. On this side, you can have water, for example. Or sometimes in process industry, we want to pressurize a material or a substance of a fluid nature, which is again not compatible with certain parts of the system. We use a separator like that to do the arrangement. Or another example of that would be, for example, a compensator in a subsea operation. We use this arrangement to achieve that purpose. But HYDAC has got some patented solutions, in the space shuttles and aerospace industry that has that arrangement. You can see this is a media separation element. We've got two different fluids coming through, and you've got the separation element in between. So thank you very much for your attention and listening to this webinar. There is a lot to cover. If you're interested to learn more about the accumulator simulation program or more about accumulators applications, please feel free to contact us. We've got a designated training designed for that purpose. You can join that training and expand your knowledge there. And you can refer to the content of this material that we presented today, or contact us at HYDAC for any if you've got any queries on that one. This webinar will be available on our YouTube channel and social media channels. So if you didn't have a chance to see it online, feel free to jump on YouTube in a few days' time, and you can rewatch this webinar in your own time. Thank you very much, and stay safe. Have a good day.